Hello, this is Thursday's lecture for week 14. We're covering section 5.2 of the EP Discrete Math text on proof by induction. And Anthony Ralston, one of the pioneers of computer science and computer science education, said that proof by induction is the standard proof technique in computer science. And you'll also find that it's maybe one of the most common proof techniques in the pure mathematics also. Anthony Ralston was famous for saying in the 30s that we should stop teaching calculus and we should just teach discrete math because it's the math of the future. I'd like to know what you think about that. Right, so after you read the EP text, and I highly recommend that you read section 5.2, she presents the standard proof by induction methodology, and that's the way it was first presented to me, and I found it rather confusing. And now I've developed a different understanding of it, which I'd like to present you here, and I hope you will agree that it's not as difficult as conceptually it's not as difficult as is often presented, and I hope to convince you of that. So there's really just a three-step technique for doing proof by induction. The first one's given in the problem statement. You just write down the nth term of the predicate. For example, it'll say prove that 1 plus 2 plus ... which means and so forth, an ellipsis, plus n equals n times n plus 1 over 2. And famously Gauss, when he was young, his elementary school teacher asked the class to add up all the numbers between 1 and 500 while the teacher went out and got a cup of coffee or something. And Gauss came up with the answer in less than 30 seconds just by realizing that you could pair all of the numbers in that series. For example, if you wanted to add all the numbers between 1 and 500, you could say 1 and 500, that's 501, and then 2 and 499, that's also 501, 3 and 498, that's also 501, and so on. So you have 250 of these pairs that all add up to 501. So the sum is just 500 divided by 2, 250 times 501. So this is actually something that will be useful to you, at least for the homework, and maybe the other times, is the sum of a series. The sum of the first n numbers is just n times n plus 1 over 2. And you have something similar for the product of the first n numbers, which I'll show you. Or in fact, the sum of any geometric series. Okay, so the first step is given to you by the problem statement. And then we just have to add 1 to n, and to show that if this is true, if this statement is true, then the statement is true when you have n greater than 1, n plus 1 on both sides. So all I've done is I've added n plus 1 to the series on the left, which is just like taking the original series and adding 1 to it, and then instead of n, wherever I had an n, now I have a, actually I can draw that in. Maybe I can't. Well, anyway, wherever you had an n, now you've... my thing's not working, no. Okay, well, wherever you had an n, now you've got an n plus 1. And you just FOIL that out, you get n squared plus 3n over 2. And I'll show you an easier way to do this in a second. But you can just do the same algebra on the left. So, but the important takeaway is just add a 1 to n on both sides, and then do some algebra to show that those statements are equivalent. And you'll notice I made this substitution here. I said 1 plus 2 plus ... n is n times n plus 1 over 2, which is what's given in the problem statement. So I'm not doing anything new here. I'm just saying that if this is true, then it's also true for n plus 1. So this is a way of showing that if it's true for one term, it's true for the next. So now, let's go backwards. I was going to say, mathematicians don't like to say that. Going backwards doesn't sound like you're actually making any progress. So let's say that we're making progress in reverse, or regressing instead of progressing. So let's regress one step. Instead of this term is equal to, if one term is true, then the next is true. We'll go backwards. We'll say if the previous term is true, then this term is true. And you can just keep doing that, right? You can just keep going backwards from the previous term all the way until you get to the first term in the series. And then, so Fermat called this the infinite descent or infinite regression. So now if you look at your rules of inference from your handout, you'll notice one of them is the transitivity. And transitivity said, if P then Q, and if Q then R, these are the major minor premise, then if P then R. So that was transitivity, and if you understand transitivity, then you can see that if P1, then P2, and the next step would be if P2 then P3, leads to an infinite series of transitivity statements where you can conclude that if P1 is true, then Pn is true. So this is, to me, the crux of the argument for proof by induction, is that if you can show that this relationship, that if it's true for one element, it's true for the next, that means that if it's true for the first element, it's true for any element. So all that's left to do is proving that it's true for the first element. And that's typically the easiest thing to do, right? If you just look at the n equals 1 term in here, it's just 1 on the left-hand side, and substitute n equals 1 on this expression, you get 1 times 1 plus 1 is 2. 2 divided by 2 is 1, and so you have 1 on both sides. So that's why Epp and other authors typically say, what we do first is we show that the first term in the series is true, and then we show that if it's true for one term in the series, it's true for the next, and then we conclude that therefore it's true for any n. So that's the formal way to describe proof by induction, to prove something by induction. But in practice, I think I showed you what we actually do, is you do some algebra to show that if it's true for one term, it's true for the next, show that it's true for the first term, and then you're done. You can just say, therefore, p to the n is true for any n by induction. And also, I should put a box around here, because these are the two kind of theorems from the chapter. We just talked about the first one, which is the sum of the first n numbers is just this, and then this is the sum of a geometric series. Okay, if it's not clearer than the homework, at least it's shorter than the homework. I think you will agree with that. But I'd like to demonstrate this technique with some of the problems that were given in the homework. And I'm also going to use another shortcut, which is using the recursion trick from last section. And the recursion, if you remember, last section we said for to use we used a recursion form of the summation to define the summation. And one thing we could do, for example, is if you have a summation from 1 to n plus 1, you can turn this into the sum of two sums, one where you have k going from 1 to n, and then you can just peel off this last term, the sum from k equals n plus 1 to n plus 1 of 5k minus 4. And you know that just by the recursive definition that when you have the sum from k equals m to m of k to the m, it's just k to the m, right? It's just almost kind of obvious. There's only one term in the sum. So this is all I'm doing here, is I'm turning this summation into the previous sum that we had, k equals 1 to n, plus the last term. So just plug in an n for the last term and you get this. Plug in an n plus 1 into the last term and you get this. So I think that makes these problems super easy. If you have to prove this, 1 plus 6 plus 11 plus 16 plus ellipsis all the way to 5n minus 4 is equal to this, then I'm lazy. I don't like to write out all these terms in the ellipsis, so I just write this in summation form right away. And this is easy because the last term in the series is the formula in the summation. Why? Because there's only one variable, and there's only one way to make the last term in the series, to make this formula look like the last term in the series when k is equal to n. This is the only way to do it. And so you'll find in this section it's going to be very easy to write the summation relations because there's only one variable to talk about. Alright, so we'll try that for another example. The second one, we have to prove that this sum is equal to n over n plus 1. Well, I'm going to use the formula for the last term again. There's only one variable, so it's easy to write this in summation form. So the summation is k equals 1 to n of 1 over n times n plus 1. So to do my proof by induction, first I have to show that it's, well, I say last, you have to show that it's true for n equals 1. So that's easy. The first term is 1, 1 over 2, sorry, the second. And on the right, if you plug in n equals 1, you get 1 over 2. So it's true for the first term. So let's show that if it's true for one, it's true for the next. And the way to do that is, in red here, instead of n, I just replaced it with n plus 1. So the series goes up to n plus 1 instead of n. And on the right-hand side, instead of n, I made it n plus 1. So now using recursion again, this is the sum of two summations. The first one is k equals 1 to n, which is this statement, n over n plus 1. And then the second one is just the last term. So the last term I plug in n plus 1 for n, and I get this. Now you just do some algebra, you show that those two are equivalent, and your proof is complete. Isn't that great? I mean, this is a 3-line proof basically, so it doesn't have to be difficult. Alright, this is a variation on the problem that Gauss solved. Add up all the numbers except for the first 7. Add the first 500 numbers together except for the first 7. So using our rule for the sum of the first n numbers, that's theorem 5.1.1, I can break this up into 2 different summations. First I have the sum from 1 to 7, and then I have the sum from 8 to n. So I can solve this pretty easily. I just plug in 7 for n in this formula, and I get 7 times 8 divided by 2, or 28. Right, it's 56 divided by 2, yeah, 28. And then I have, this is what we're trying to solve, the sum from 8 to n. So all I need to do is take this on one side, subtract this from both sides, and I have my closed form solution, which looks like this: k times k plus 1 over 2 minus 28. Yeah, closed form just means that there's no summation symbol and there's no ellipsis. So this is the trick for at least 3 of the problems, is realizing that you can take your series and break it into 2 different series, one of which you're trying to solve for. Alright, and then lastly, number 8, I found this to be a challenging problem. The question is, actually this is, she's sort of cheating a little bit, right? But the problem might be stated: find the product of this sequence. We have to find the product of this sequence. And I've just used because I'm lazy and I don't like to write all this out with the ellipsis, I've just written this in pi form now. Right? I can use this last term as the formula for my my product. It's just the products of from k equals 1 to n of 1 plus 1 over k. And then I'm going to see if I notice a pattern just by trying this for small values of n. So when n is equal to 1, it's just 1 plus 1 over 1, which is 2. And then when I have n equals 2, I've got my original term, 2, times the next term, which is 1 over 1 plus 2, so 1.5, times the previous term gives me 3, and then I do that 2 more times. And I see that it's just going up by 1 every time. In fact, the answer is just 1 more than n. So my guess is that maybe the product is just n plus 1. Well, this is just a guess. I've just looked at the first 4 terms. And there's some famous examples where things start to look really good, like prime number generators is a really good example of this, where a prime number generator appears to work for the first 5 or 6 terms, maybe even the first 11 terms. And so we start to develop this strong suspicion. I mean, if it were a courtroom, it would be the guilty verdict would definitely be handed down, because it's an overwhelming preponderance of evidence, right? You tried it for 11 different times and they worked every time. It must be true. Well, math, that's not good enough. We have to show that it's good for every possible n. And so let's do this. Let's do the proof. So I'm using proof by induction again. Here's my first step. I write it down for the nth term. Ignore the red for a second. Now I just add 1 to n. So now instead of doing the series from 1 to n, I do it from 1 to n plus 1. I'm using my recursion relation again. This is equal to the product from k equals 1 to n of 1 plus 1 over k, which we know is n plus 1 from the problem statement, and then times the last term. So the last term, I just plug in an n plus 1 for k, and I get this, 1 plus 1 over n plus 1. And on the right-hand side, I just add 1 to n also. So now the problem comes down to showing that these two are equivalent, and that'll take you 2 lines of algebra, and you'll see that those are actually equal. And I haven't been emphasizing this, but remember, for all of these problems, the first step or the last step, if you use my method, is that you have to show that it's true for the first term, and we did this already, right? We showed that it's true for the n equals 1 term. Okay, hopefully that helps you with the homework. If not, please call or text, and I'm sure we can work it out. Thanks.